Hello, we're going to go over Honors Chemistry Chapter 2. We're talking about significant figure in measurements today. Quick reminder that for these prefixes, you guys need to memorize the example column. If you don't already know how many meters are in a kilometer or centimeters in a meter, make sure you go through this, make some flashcards, and memorize these over here because you're going to need to be able to convert between these quickly. You can also use your notes on the test, so if you want to write them down, you can do that, but you should be able to remember what giga, mega, kilo, deci, centi, milli, micro, and nano mean. Pico we use sometimes, but usually we stop at nano. Okay, so make sure you study these example amounts for the prefixes for our units. All right, so we talked about taking measurements and recording all of the numbers that you can see, so the 20, the 21, and estimating that last digit. Looking at this ruler, we are going to write down our best estimate for the measurements A through G. Okay, so remember that we are going to read all of the lines on this meter stick here, or this ruler, and we are going to estimate a last digit. So for A, it's definitely between the 1 and the 2, and I can read clearly that it is very close to this. It would be 1.1, 1.2, 1.3, 1.4, 1.5. Okay, so A is very close to 1.5, and we're going to estimate. Do we think it's slightly before, slightly after, or right on the line? I would say it's right on the 1.5 line. So this 0 right here is going to be a significant figure. It is telling us that to our best estimate, that measurement is right on the 0.5 line. For B, it is between the 2 and the 3, so it's definitely 2 point something. We can count the lines. We can count the lines over here. So this would be 2.5, 2.6, 2.7, 2.8. I would say that that is just before the 2.9 mark. So 2.85. And these are, we're measuring these in centimeters. Always put your units. That was a bad example. Okay, so I'm estimating this last decimal. You might have estimated it as 2.88 or 2.89 or 2.86. Any of those is acceptable. So as long as we know that it's after the 2.8 line, but before the 2.9 line, then we have an accurate measurement. So we have to have these 3 digits in our measurements here. Okay, so over here, the next one is, I would say it's just slightly past the 4.2 mark. So 4.2 and a little bit past there, I'm going to say 1. So this 1 is significant. It's telling us it's just slightly past the 4.2 mark. Okay, for D, For D, I would say it's right on the line. So it's 5.1, 5.2, 5.3, and I'm going to report that it is right on the 5.3. The way that we show that it's right on this line is with the 0 at the end. Okay, E looks like 6.60 to me. Centimeters. Okay, and F appears to be 8. It's not quite at the 0.1, so it's slightly before 8.1. So let's say it is 8.08 centimeters. This is my estimation telling me it's not quite to the 0.1 mark, it's just right before that. And last but not least, for G, I would say that it is just slightly before that 12, so 11.99. 11.99 centimeters for measurement G. Okay, so what does this have to do with significant figures? That's what we're talking about today. Significant figures tell us which numbers were actual measurements and which numbers are just placeholders. So there are 3 rules that you must memorize for significant figures, and they are right here. All non-zeros are significant. So if I'm looking at A, that means the 1 and the 5 are significant. Rule 2, trailing zeros. That means a 0 on the right of a number. So this is a trailing 0. After a decimal are significant. So it has to meet both criteria. It has to be on the right side of a number and it has to follow a decimal. This meets both of those criteria. It is on the right side of the 5 and it's after this decimal. So this is a significant figure. And the third rule is probably the easiest rule. If you have a 0 between 2 significant digits or figures, it's also significant. I call this the sandwich rule. So if we have a 0, here's a sandwich. This 0 is sandwiched between the 2 8s. That means that this 0 is a significant figure. Okay? When we add and subtract numbers, so if I was adding up the, let's say we're doing the area, the perimeter, and these are all 1.0 centimeters, I would have 1.0 plus 1.0 plus 1.0 plus 1.0. We're going to add this all up, 4.0. This answer should have the same number of decimal places as all of our measurements. So since we had 1 decimal place in each of these, we want 1 decimal place in our answer. That's what this rule is telling us. And the multiplication and division rule says that if we are multiplying or dividing numbers, then the answer, the answer should have the same significant figures as the measurement with the fewest. So if instead of finding the perimeter, we were finding the area, length times width, and let's make them 4.0 centimeters. I should have put centimeters on all of these. And 4.0 centimeters. What is the area inside? That's length times width, which is 16. And here's the tricky part. You might want to put 0.0, but this has 2 significant figures, so that means that my answer inside should have 2, and this already has 2 significant figures, and that is centimeters squared. Okay, we have to do some examples for that to sink in. All right, so here are a whole bunch of measurements, and we're going to go through the list and write out how many significant figures each number has. So 5.0, this is a significant figure because it's not 0. This 0 is on the right side of a number, so it's trailing. Okay, it meets that rule. And it's after a decimal, so it is a significant figure. So this has 2 sig figs. Number 2, 100. The 1 is significant. These zeros are trailing because they're on the right side of the 1, but they're not after a decimal, so these do not count. So this one just has 1 significant figure. And if we were making a measurement like on a meter stick, we wouldn't be able to estimate anything. So we would just be saying, okay, it's somewhere between like 0 and 2. So it's 200. So we're gonna say it's halfway, it's 100. So that would be, we're not sure about either one of these zeros here. Okay. On the other hand, this number looks very precise, like a measurement that was taken with a really precise instrument to know it to 2 decimal places and have it be this big of a number. We would have to have a really, really sensitive, let's say this was grams. We don't know what it is, but let's say it's grams. This would have to be a really sensitive balance for us to get that reading. So let's talk significant figures. Anything that's not 0 is significant. These are trailing zeros. They're on the right side of the 6, and they are after this decimal right here. So these are both significant. So this one has 6 significant figures. That's a lot of significant figures. 4 is 3, 4, 8, 0, 7, 6. All of these are significant because they're all non-zeros, and this 0 sandwich rule is between the 8 and the 7, which are significant, so it's also significant. So this one has 6 sig figs. 3 and 6, yeah. Number 5, 2, 6, 5, 0, 0, 2, 7.0. So anything that's not 0 is automatically significant. These are sandwiched in between, so both of them are significant. And this trailing 0 is after a decimal, so this one is also significant. So this one has 3, 6, 7, 8 significant figures. All of them are significant. Number 6, 75.00. These two trailing zeros are after the decimal, so they are significant. This one has 4. Number 7, 10.00. This one's trying to show you that these trailing zeros after the decimal are significant, and this 0 can be sandwiched in between them. So this one's also significant. So even though these are zeros over here, it's still significant. So this one is sandwiched. So this one has 4 sig figs. Number 8, 5.600. These are significant. These zeros are trailing and after a decimal, so they're also significant. So this one has 4 as well. Number 9, 12.001. All non-zeros are significant, and these two are sandwiched in between. So this one has 5 sig figs. And number 10, 40. The 4 is significant. This trailing 0 is not after a decimal, not significant. This only has 1 sig fig in the answer. Okay, so moving into accuracy and precision. Accuracy is how close your measurement is to the accepted value, and precision is how close together a set of measurements are to each other. So if we were doing a lab, sometimes we do a specific heat lab where we calculate specific heat, or density lab if we find the density of metals. Density of metals. We might be working with zinc and copper and iron and aluminum. Okay, just for example. I'm going to look up their actual densities so I can estimate what the measurements we would get might be. So let's look up density of zinc, 7.140. So this would be 7.140 grams per milliliter. That's mass over volume. Density of copper, 8.96. 8.96. Notice it said grams per cubic centimeter, and this one said grams per milliliter. 1 cubic centimeter, we also call these cc's, like in the hospital. Cc's are cubic centimeters. 1 cubic centimeter is 1 milliliter. They are the exact same volume, so we can use these interchangeably. Okay, let's do iron and aluminum. Iron, 7. I'm going to round it off, 7.87. And then aluminum, 2.7. 2.70 grams per cubic centimeter. Okay, so now that we have an idea of what they should be, let's say we did a lab and your group was assigned aluminum. So you had to find the mass and the volume of your piece of aluminum and calculate its density by dividing the mass by the volume. And you found that the answer was 2.60 grams per cubic centimeter. I would say that that is a pretty good job. Okay, so we'd all be happy with those results. We would say that this is fairly accurate. Okay, that is an accurate measurement. Okay, it doesn't mean to say that if you don't get an accurate measurement that's a bad thing, because sometimes when we don't get the results we expect, we actually learn more than when it goes just as planned and we get whatever results we were expecting. Okay, now the group next to you, they were assigned iron, so they had a piece of iron and they had to find the density of iron. They found that it was 6.50 grams per cubic centimeter. That's a pretty big error between 7.87 and 6.5. So I would say that this is not accurate. This is inaccurate. Okay, that's inaccurate. And then they would have to figure out, well, why is my density so much less than it should be? Either the mass was measured as being too small or the volume was measured as being too big. Okay, so this would be inaccurate. Now, we decided to fix the problem, and we are all going to measure the density of iron. And we all found, so let's say group 1 found 6.49, group 2 grams per cubic centimeter. Group 2 found that it was 6.51 grams per cubic centimeter. We had the 6.50, and then we had another group that was also 6.49. Okay, so these measurements, though they are not accurate, they are not really close to the 7.87 that they were supposed to get. They are all very close together to each other. Okay, so these are close together. The group of measurements that we took as a class in our imaginary lab are close together. These are precise. Okay, precise is how close together the measurements are. They're inaccurate, but they are precise. Okay, and let me go back over here. So accuracy is how close it is to the accepted value. Precision is how close the set of measurements are to each other. If you can see our little dartboards here, these are all bullseyes. So we threw a bunch of darts and they all hit the bullseye. We are precise, it says yes, and accurate, yes. So this is high precision and high accuracy, okay? This one, notice that they threw kind of just randomly all over. So we had one that was way too high, one that was way too low. But what would happen if I averaged this high and this low? We get this wider curve here, but it still has the high point at that accurate value. So the average, basically, of all of these is the target. So that's why this can be accurate and not precise. Okay, when they average out to be accurate. So if somebody got too high and another group got too low, and somebody got an accurate measurement, all three together might give you a correct density over here. Okay, so let's look at, this is our class example. We had good precision. So yes, it was precise. No, it was not accurate. So this person is throwing the darts and they're all landing in the same area, but it's not where they want them to be. It's not at the target, it's over here. Okay, so this is precise, not accurate. And then lastly, this is like the worst case scenario. They're all over the place and they're not accurate. So if our measurements had been just all over the place, we wouldn't really be able to pinpoint what the error is, and we're not getting good results either. So this is not a happy situation right here. Something is wrong with the lab. Okay, so why do we have all of these differences in measurements? There is a random error that happens in every single lab. So if you take let's say you're taking your weight and you take it twice, you might get two different readings. That has to do with random error. If you're taking the mass of zinc and you take it 3 times, you might have 3 slightly different measurements. They're going to be very close, but they might be just a little bit different. Okay, so we might get, for example, like 60.1 60.2 grams, and then 60.14 grams, okay, or 60.11 grams. So they're very close together, but you're going to get 3 different measurements because of random error, okay? And so which of these bullseyes looks like random error? Bullseye 1, bullseye 2, bullseye 3, or bullseye 4? Okay, bullseye 2 looks like it has a good amount of random error. So it has an equal probability of being, of being too high or too low. And they usually they usually balance out. So let's see. It has an equal probability of being too high or too low. Almost all measurements have some degree of random error. This is why the balances move up and down, and they will average themselves out in your measurements. A systematic error is different. This is an error in the system that's going to result in your data being either too high or too low consistently. A systematic error does not average out with repeated trials. So if I averaged where this was landing, there's nothing that can average it to be over here in this accurate position. Okay, so this dartboard 3 shows systematic error, where it's consistently too low and over here on the left-hand side. Okay. And also notice even where all of them land in this bullseye area, they're not all one on top of each other. So that tiny bit of difference, even this one still has random error. Okay. All right. So that is it for these notes. Have a wonderful day.